All right, let's look at one now that has both t and y in it, and the coefficients being non-zero. Again, we look at these slopes for t between 0 and 2 and y between -1 and 1. Now here we kind of do have to plot vectors at each of those 9 points and look at them independently, because anytime we change t or y, we're going to change the value of the slope. So here I'm just going to go ahead and write out this entire table, and it's going to be the difference between half of t and half of y. So if I start down here at 0, -1, that's going to give me a slope of, let's see, 0 minus a half times -1 is going to be positive a half. And I'm just going to continue doing these. So 0, 0 will give me a slope of 0. 0, 1 will give me a slope of negative a half. So that means that negative a half, so that would probably look something like this. It'd be positive, oh sorry, that's down here though. That's down here at positive a half, so I want it to aim right about there. You can see this gets very tedious now. 0, 0, there's a horizontal slope. Here there's a negative slope. Negative a half, I want it to aim right about there. And now when I change t to 1, I'll look at 1, -1, 1, 0, and 1, 1. So at 1, -1, that will be a half plus a half, which is 1. This will just be a half. And this will be a half minus a half, which is 0. So those slopes will look more like this. So at 1, -1, I'll have a slope of 1, so it'll aim right up there. And here I'll have a slope of a half, which will aim right about there. And here I'll have a slope of 0, which will look horizontal. And finally, we look at when t is 2. So we'll look at 2, -1, 2, 0, and 2, +1. So when t is 2, that's going to give me an output of 1 for 0.5t. When y is -1, that'll give me an output of positive 0.5, so this should be a slope of 1.5. This will be a slope of 1, and this will be a slope of, let's see, 2, it'll be 1 minus a half is going to be a half. So at 2, -1, I'll have a slope of 1.5, which means I want to aim for right about there. At 2, 0, I'll have a slope of 1, which will aim right about there, a little less inclined than that one. The slope of a half will aim more horizontally, less vertically. And I can already kind of see what's going to happen to an initial condition. If I pick that one, gosh, it looks like it might even do something like this and then come back up. And then maybe an initial condition here will probably start to also grow upwards here. These will kind of grow upwards. So it looks like ultimately all of these initial conditions will start to move upwards. Again, this is a very limited picture, so what we observe here is just based on these 9 slope segments. Another thing that we could do to make the slope field more precise is to populate it with vectors even in between the integer values. So there's no reason why we couldn't have looked at the slope at the point, say, 0, positive a half, or 0.5, 0.5. There are really infinitely many vectors that we can generate within this plane. But we wanted to keep this simple since we are doing this by hand initially. So one thing to notice that now that our differential equation depends on both t and y, the slope segments change when either or both t or y change. So we don't see this consistency in having the vectors vertically be the same or the vectors be the same along rows. We now kind of notice that it looks almost like a random scatter of vectors. So slope fields are powerful to help us visualize the solution space. That is, we didn't just look at, we're usually interested in some particular initial condition, but we also get the bonus of seeing how all solutions around it behave over time. It's powerful and it extends broadly, because if you're trying to do a kind of a general analysis, or to say, well, how do initial conditions evolve differently, you can see that with the slope field. You don't get the exact solution, and I don't know that this curve swings up as quickly as I made it swing up. Maybe it takes longer, and maybe Maybe it's even more flat. Maybe it looks more like this for that initial condition. But again, this is a qualitative analysis. It's just to describe the qualities of the solution. Now, of course, it would become painstaking to sketch not only accurate, but also all-encompassing slope fields. Technology is much more efficient in doing this for us. And there are many slope field applets out there. This is one that's simple and readily available, so we're going to go ahead and use this one. What this one shows you is, first of all, you want to make sure this is set on 1 ODE. We won't use the polar stuff. We'll eventually use systems. Here they use y and x as the dependent and independent variables. To be consistent with our notation, we could use dy dt. And let's just go ahead and plot the first slope field, which was 2y. Okay, so here we have it, and that looks very similar to what we came up with before. But you see that we have, and we want to limit ourselves, let's say, from t is 0 to 2, as we did in our sketch, and y going from -1 to 1. Now, obviously, this has a lot more vectors populated in there, but you see they follow the general behavior. And I could reduce the number of segments that I have along the t-axis. This is 1, 2, 3, 4, 5 columns of vectors. If I just wanted to do, oh, it won't let me do a 3 by 3. The lowest I can go is 5. So, but there you go. That looks very similar to what we had before. Now, the more slopes we put in there, obviously, might say, well, the more the better. But it starts to get kind of unnecessarily dense. Maybe up to about 30 it looks good. You can also, we'll talk more about this in here, what it means to use Euler, improved Euler. These are numerical techniques. But if I enter an initial condition, like for example, 0, 0, and I press submit, that will actually sketch the solution curve using a numerical method, which we haven't covered yet, but we will in a soon-to-come lesson. I could actually look at different initial conditions in here. Maybe 0, 1/4, which I expect to kind of go up and to the right. Oh, see, my sketch with my cursor was a little bit more exaggerated. And you can also actually click in here, and it will show you where that trajectory goes. So you can see how these curves appear to just be horizontal shifts of one another. If I change this to 2t, it uses those same initial conditions, but with 2t we saw that those are just vertical shifts of one another. If you want to make this more precise, you can change this to Runge-Kutta-4, RK4. It's just a more precise technique, and the curves look much more smooth with that.